Hello friends, in this lecture we are going to discuss about reactions of pyrrole. So pyrrole is a 5-member heterocycle with nitrogen as an heteroatom. So the electrophilic substitution reactions for pyrrole, that pyrrole is a pi-accessive aromatic heterocycle which contains 6 pi electrons, 4 pi electrons on 4 carbon atoms and 2 pi electrons on 1 nitrogen. The pi-accessive characters of pyrrole makes it susceptible towards electrophilic substitution reactions rather than addition reaction. So due to the presence of the pi electron, that is 6 pi electrons, it becomes more susceptible towards substitution reactions. Pyrrole undergo electrophilic substitution preferentially at carbon 2, providing thermodynamically stable product, although the substitutions at carbon 3 is also favorable in some kinetically controlled reactions. Most probably the reaction takes place at carbon 2, but in sometimes reactions can proceed at carbon 3. The preferential substitution of carbon 2 alpha, that is alpha position, that is carbon 2, rather than at carbon 3, that is beta position, may be rationalized by higher stability of the transition state, that is sigma complex, resulting from the electrophilic attack at carbon 2 than that obtained by electrophilic attack at carbon 3. The transition state, that is sigma complex, involved in C, that is alpha position. Substitution is therefore stabilized to a greater extent than that involved in C3, that is beta substitution. So keep it in mind, substitution takes place at C2, that is alpha position, rather than C3, that is beta position. Okay. The substituents attached to the nitrogen atom of pyrrole position 1 do not have an appreciable effect unless they are bulky or strongly electron releasing or electron withdrawing substituent. The presence of bulky group exerts steric hindrance and directs electrophilic attack at position 3. So due to the presence of bulky group, which exerts steric hindrance, and that's why the reaction takes place at position 3. The position 3 substitution increases with increasing steric effect of the substituent at position 1. So these are all different positions on which the electrophilic substitution reactions are possible. Then electron releasing substituent at carbon 2. Due to the presence of electron releasing substituent at position 2 of the pyrrole ring, electrophilic substitution at position 5 is an alpha position, that is alpha dash, while the presence of substituent at carbon 3 causes substitution at position. Electron withdrawing substituents at carbon 2 results in electrophilic substitutions at both carbon 4 and 5. But the ratio depends upon the M mesomeric effect of the substituent as a proportion of 4 isomer increases with effect. The presence of electron withdrawing substituent at carbon 3 facilitates the attack of electrophile at carbon 5. Nitration. So now we are going to see the reaction of pyrrole, this nitration reaction. Because of the sensitivity of the pyrrole ring to oxidation and acid catalyzed dimerization and polymerization, pyrrole is not nitrated under strong acidic condition. In strong acidic condition, nitration reaction is not carried out. The reaction of pyrrole with nitratic mixture, that is concentrated HNO3 plus concentrated sulfuric acid, suitable for nitration of benzenoid compounds, results in its extensive decomposition. And pyrrole is nitrated by nitric acid in acetic anhydride. Which is reacted with HNO3 first. Then the product which is formed by reacting these two reagents is treated with pyrrole, and it gives substituted pyrrole at second and third position. So pyrrole is nitrated by nitrating nitric acid in acetic anhydride at low temperature with the formation of 2-nitropyrrole as a major product together with 3-nitropyrrole. So 2-nitropyrrole is the major product which is formed in this reaction. Nitration of substituted pyrroles. So this one is substituted pyrrole at first position by acetyl nitrate. So this one is acetyl nitrate. It also provides 2 and 3 nitro derivatives. So in this case also we'll get two product, that is 2-nitropyrrole and 3-nitropyrrole. Is favored steric effect of the substituents at position 1. Then halogenation reactions of pyrrole. The high reactivity of pyrrole ring system causes it to undergo halogenation at all the strongly activating position. The special reagents with mild conditions are therefore required for the halogenation. Chlorination. Chlorination of pyrrole with sulfuric chloride in ether results in polychlorination providing diet, and finally pentachloropyrroles depending on the quantity. Chlorination of pyrrole with elemental chlorine in warm aqueous alkali produces 3,4-dichloromelamide, which is considered to be derived from the soluble okay. So in further reaction we'll see 131 structure, that is 3,4-dichloromelamide. So in presence of SO2Cl2, okay, when there is 1 mole of SO2Cl2, it gives monosubstituted product, that is 2-chloropyrrole. And further in subsequent more harsh condition or more excess SO2Cl2, it gives substituted chlorine group at 2nd, 3rd, 4th and 5th position with chlorine group. Okay, then excess SO2Cl2 second hydrogen atom with chlorine. Similarly, there are number of internal rearrangement reaction takes place, and then further with the removal of water molecule, it gives this product which contains oxygen group at 2nd and 5th position. Then bromination. Bromination of pyrrole with bromine in acetic acid gives 2,3,4,5-tetrabromopyrrole. Okay, 2,3,4,5-tetrabromopyrrole means what? There is an addition of bromine at 2nd, 3rd, 4th and 5th position. But pyrrole substituted with electron withdrawing substituent undergo bromination providing monobrominated pyrroles. However, with bromine in carbon tetrachloride, 3-bromopyrrole is obtained by the isomerization of thermodynamically less stable 2-bromopyrrole. So this is the reaction of pyrrole with bromine. So in presence of CH3COOH, it gives 2,3,4,5-tetrabromopyrrole. Okay, if second position is substituted, then bromination takes place at 4th and 5th position. Okay, so there is addition of bromine at 4th and 5th position. Further, addition of Br2 in presence of CCl4 gives intermediate product which has bromine attached at 2nd position, and then further on reaction it gives 3-bromopyrrole. So these all are bromination reactions of pyrrole. Then iodination reaction of pyrrole. Then iodination of pyrrole with iodine in aqueous potassium iodide provides tetraiodo-pyrrole. So this one is tetraiodo-pyrrole. That is 2,3,4,5-tetraiodo-pyrrole. However, iodination of pyrrole substituted with electron withdrawing substituent at position 2 results in the substitution at position 4. So due to the presence of this substituent, which is electron withdrawing in nature, then iodination takes place at 4th position. And pyrrole 2-carboxylic acid. Okay, this one is pyrrole 2-carboxylic acid. Polysubstituted by electron withdrawing substituent undergo iodonative decarboxylation to provide corresponding to iodopyrrole. Okay, so it is an corresponding decarboxylation, iodinative decarboxylation. So COH group is removed out, and this position is attacked by iodine. And product will get iodine at second position instead of COH, because COH removes out and this position is takes place by iodine. Pyrrole and its N and C alkyl pyrroles cannot be sulfonated under ordinary conditions, as these are realized by concentrated sulfuric acid. Therefore, sulfonated by mild sulfonating agent. So keep it in mind that for sulfonation of pyrrole, mild sulfonating agents are required. It is pyridine in sulfur trioxide. Pyridine in sulfur trioxide, which is used as a reagent for sulfonation of pyrrole. So it gives low acidity to the reaction condition. So the reaction of pyrrole with pyridine sulfur trioxide complex at 100 degrees Celsius provides pyrrole 2 sulfonic acid. So this is a pyrrole 2 sulfonic acid, in which we get an intermediate product which contains pyridine sulfur trioxide attack at pyrrole second position. If further, due to the presence of hydrochloric acid, hydrogen attacks on oxygen and forms SO3H, and this pyridine removes out, and then we get the pyrrole substituted with SO3H group in second position. Then pyrrole substituted with electron withdrawing substituent requires vigorous reaction condition: chlorosulfonic acid, concentrated sulfuric acid, and oleum. If both the alpha positions are blocked, the sulfonation occurs at beta position. So in this case, both the alpha, that is alpha and alpha dash positions, both are blocked. So reaction takes place at beta position, that is at third position. Then acylation reaction of pyrrole. Acylation of pyrrole produces N-acyl or C-acyl pyrroles depending upon the reaction condition. Acylation of pyrrole with acetic anhydride at 100 to 150 degrees Celsius affords 2 acyl 143. So this is an 143 and 144. Okay. 2,5-diacyl. This one is 2,5-diacyl and this one is 2-acyl pyrrole. But pyrrole with acetic anhydride provides N-acyl pyrrole. So in first reaction there is an C-acylation, and in second reaction there is an N-acylation reaction. The difference is presence of sodium acetate. Due to the presence of sodium acetate, it gives N-acylation. Then N-acyl pyrroles can be obtained by the alkali metal salt of pyrrole with a acyl halide. So this one is an alkali metal salt. Okay, in presence of this alkali metal salt and acyl halide, that is RCOCl, it gives an acylated form of pyrrole. Then Ketterman formylation. The reaction of pyrrole with zinc cyanide and hydrochloric acid results in C formylation involving attack of iodoformyl electrophile at position 2, that is alpha position. So formylation is addition of formaldehyde group. Okay, so Ketterman formylation reaction is conversion of pyrrole into pyrrole 2 carbaldehyde. So zinc CN2 twice. Okay, zinc cyanide and HCl. There is an addition of CH double bond NH at second position, and then the removal of both water molecules forms pyrrole 2 carbaldehyde. If both the alpha positions are occupied, then C formylation occurs at beta position, but electron withdrawing substituent at alpha position inhibits formylation. So for that, alpha positions are occupied, C formylation occurs at beta. Formylation is very significant reaction in pyrrole chemistry because of the use of pyrrole 2 carbaldehyde in porphyrin synthesis. So in porphyrin synthesis, pyrrole 2 carbaldehyde is used as a precursor. So these are the reaction in presence of zinc cyanide. It gives a formylation reaction, that is formaldehyde attack. So when all three positions are blocked, the reaction takes place at fourth position, and in this case there is no reaction. The nucleophilic substitution reaction. The pi electron character of pyrrole renders it relatively inert towards nucleophilic substitution for addition reaction. The nucleophilic substitution reactions are rare in pyrrole, however, pyrrole is prototypically with electron withdrawing substituent. Keep it in mind, for pyrrole, nucleophilic substitution reactions are very rare, and this is because of its electron withdrawing substituents are not detected only in pyrrole because protonation magnetic. For that, if you want pyrrole and nucleophilic substitution reaction, then it must require that pyrrole is substituted in substituent. And photooxidation, that is photosensitized oxidation of pyrrole. That is photosensitized oxidation of pyrrole produced 5-hydroxy delta 3 pyrroline 2-on. Okay, solution hydroxy group is present, that is 5-hydroxy, and in third and fourth position there is double bond is present, that's why it is delta 3 pyrroline. Structure is for pyrroline, and at second position double bond O is present, that's why it is 2-on. So this is the structure of 5-hydroxy delta 3 pyrroline 2-on via the 2,5-peroxide intermediate. So this one is peroxide intermediate, that is 185, involving 4+2 cycloaddition reaction. So this is overall photosensitized oxidation of pyrrole. Then oxidation with hydrogen peroxide. The oxidation of pyrrole with warm hydrogen peroxide in pyridine for a pH range of 4 to 6 produces a tautomeric mixture of pyrrolate ones, that is 185, 189 and 190. Okay, the presence of electron releasing substituents makes pyrrole susceptible to oxidation by hydrogen peroxide, while the pyrroles with electron withdrawing substituents are less susceptible to oxidation. So this is the oxidation reaction of pyrrole in presence of hydrogen peroxide, it is H2O2. Okay, so first OH groups attacks at second position, and there is a removal, there is a change or pull, there is a shifting of this. That's why we get in which the position of double bond is different. Okay, and this product is pyrrolane 2. And the reduction reaction. Catalytic hydrogenation of pyrroles can be catalytically hydrogenated at moderate temperature with the formation of pyrrolidins. Okay, so reduced form of the pyrrole is pyrrolidins. The presence of electron between and alpha and beta positions resist to the reduction of the ring, but the substituents are reduced differentially. So substituents which are present, they are reduced. So in this case, COOR is substituent reduced to CH2OH. Then further, the CH double bond CH2 is substituent reduced as CH2CH3. Then further, due to the presence of this H2 catalyst, there is a reduction in pyrrole ring instead of substituent at N. Okay, whenever there is a substitution present, reduction takes place in pyrrole ring instead of substituent. And further, reduction reduces the substituent which is present at first position on nitrogen. In this reaction also, initially the reduction takes place in pyrrole ring, and then further If reaction proceeds as it is, then further reaction takes place in the substituent, which is phenyl ring. So these are the both the reaction in which there is substituent present at first position, nitrogen. Okay, so in such type of reaction, reduction reaction initially takes place in Pyrrole ring, and then if reaction proceeds further as it is, then further reduction takes place in the substituent. Thank you.